just spend a couple of minutes on this, and it's the dielectric breakdown. So there's every material can break down for different reasons. For electrical breakdown, there can be different things. In 126, you might have read about avalanche breakdown, and it's sometimes reversible or not reversible in diodes. But in general, any material, so when we say dielectric, basically like an insulator, so even air can break down. There could be plasma generated, there could be ionization happen. Similarly, glass, water, everything can break down, plastic. And there is, in general, the simplest way to explain breakdown mathematically is just having an electrical breakdown would be a critical electric field. It may be 10 to the 5 volts per meter. It may be 10 to the 7 volts per meter. So that's E critical. If your field anywhere in that dielectric is higher than that, the magnitude, then there will be some damage. And once it's damaged, it's often not reversible. We can't reverse that damage. So for a waveguide, if we have to find out, hey, I mean, we have a mode we want to launch in the waveguide, there are two things to that mode. First is the shape of the mode. So when I say shape, it's a geometric shape, kind of. You can see the picture. But mathematically, what it means is how the field changes with the vectors, x, y, z, with position. So when we see this kind of a diagram, it shows us how the field magnitude for this particular mode, which is TE10, changes with position inside the waveguide. So in general, that's a mathematical expression. So this expression, which is math, is plotted in a pictorial form here, right? And from this picture, you can see that if you know that red color means high and blue means 0 here, green is in between, that the highest field in this is in these center regions. Now for TE-M0 modes, this is the expression. From looking at the expression, you can tell what's the maximum field for that mode. So there are two things about the mode we can launch in the waveguide. One is what kind of mode. We can choose as a source whether we want to launch TE-M20 or 30 or 40. That depends on the generator, the device that we use to generate that field. There is second aspect, which is how much of that mode or how much power or energy we want to send in the waveguide. That also depends on you as a generator of who is launching in that. You can crank up just like crank up the volume for your music, you can crank up the field. The shape will look the same. All you're doing is cranking up this amplitude. This is an arbitrary number, right? You can have this as 1 volt per meter. You can have it as 5J volts per meter. You can have this as 10,000 volts per meter. That's called the energy. So you can put 1 milliwatt of power going in there. You can put a watt. There is no limit. Depends on your source. And that's when this comes into play. So then how much is the maximum you could put in? Well, that depends on what's the critical field. So if somebody gives you the critical field, you have to be able to tell where the field is maximum. That's where the damage will happen first. And in this case, for TE-M0 modes, wherever this sign is 1, for TE-10 mode, so if I plot this, if I plot the magnitude of this field like this, and this is my x direction, which is this is 0, and this is A, right? This will be my TE10. This will be TE20. But since I am plotting magnitude, so I should have done it a little differently. It will look like this, right? Now, why am I drawing this higher or lower? That doesn't matter. It's ideally I should be if I am normalizing it. But what it shows is there are two locations where this maxima will happen for TE. This is TE10. This is TE20. TE20 will have maximum will happen here. That's where the sine term will go to 1. No matter what this, where the maxima happens, the maximum value will be the magnitude of this. But remember, this is a phasor. When we calculate the real field with with respect to for this phasor, we have to have a square root of 2. When, if you remember how to convert a phasor to a real field, you multiply by square root of 2, and then, so let's not do the math. It's easy to see that the maximum that will happen anywhere for this mode is 2 times, so this 2 times square root of 2 times this magnitude of EI0. So this is our maximum field that will happen anywhere for TEM0 mode. And as long as this quantity is less than E critical, we are fine. So that's the level we are doing. Okay, we are not doing anything more. And the second thing is, where will that happen at the? So this is for A by 2 for TE10. I should have written that. For TE10, this location will be A by 2. For TE20, this location will be, I think, A by 4 and 3A by 4 for the X direction. And you can keep on going. So any question about this? This is when breakdown will happen if you choose to launch an amplitude which is higher than this value. So in that way, so this amplitude should be less than or equal to E critical, which is a material parameter, divided by 2 square root of 2 to be safe. Let's just say that way, okay? For TE M0 mode, the way we have defined. Any questions on this? So this is something I uploaded last time, and actually that's pretty much it for this chapter. We might come back to this chapter for in the last class, maybe one class, to discuss cavities. I don't think we have the I consider transmission lines, which I want to cover it to a certain level, and we have about 10 classes left. I think little over a month, and we will have a second midterm. I don't remember the date. What we would like, maybe in a couple of weeks. I'll let you know soon. And then obviously we will have maybe a review session or something like that. So we don't have maybe probably 8 more classes. So I'd like to move to chapter 11 and 12. So 11 is field analysis of transmission lines. This chapter was chapter 13, which is waveguides and cavities. We are not doing the cavities. Basically, this is a waveguide that we do. What's a waveguide? It is of infinite length. That's something that you remember. It's some cross section. In our case, we chose rectangular cross section, but the length of the waveguide is infinite. So that's the assumption we have. That's what we call a waveguide. Now, if you cut the waveguide length, you make it a finite length, that becomes a cavity. So in general, people will put some sort of reflecting boundaries at the two ends. So make it like a box. That becomes an optical cavity. It's a very interesting thing to learn about, and that's what makes a laser, but I don't know if that requires probably at least to do some justice a couple of weeks. So I don't want to spend time on that. Instead, I would like to move to this transmission lines first, because that's where a lot of work is done. When you go out in industry, or you do study power transmission, or you do on chip, or you do high frequency device design or circuit design, or you do these data centers, and transmission lines theory is becoming more and more important to understand and know. So in chapter 13, what did we do? We did metallic waveguides, right? In metallic waveguides, that was, these are single conductor waveguides. By single conductor, I mean they are made up of a single continuous metal conductor. So it could be a circular metallic pipe. This in this case is a rectangular metallic pipe, but there is no discontinuity in that metal. So these were single conductor waveguides. They have, so I want to talk about a little bit about their limitations. And they have a size limitations for frequency you want to choose. For example, so let me just give you, these don't work at lower frequencies. So what lower frequencies and what's the limitations? Well, you kind of already saw the limitation. We derived cutoff frequencies, right? And then there is a certain cutoff frequency, the lowest for our FFC10. That was the lowest cutoff. So our frequency of radiation that we want to channel in this waveguide, it has to be greater than this frequency. So that's pretty much the answer, but I want to give you a slightly different perspective of what's the limitation on geometry of a waveguide. But this is pretty much it. We are kind of extending this discussion a little bit here. So these don't work at lower frequencies, right? So you remember for a rectangular waveguide, the frequency had to be greater than FC, F cutoff for 1,0 mode. So let's look at some different, so you all know F is related to lambda by this relation, right? 1 over inverse. C naught is 3 times 10 to the 8 meters per second. So if you look at some of the frequencies and I guess lambdas, let's look. 10 megahertz is, so the way I remember is 1 gigahertz is 30 centimeters, 100 megahertz is 300 centimeters wavelength, 10 megahertz would be 3 millimeters. So right, oh no, 10, 1 gigahertz is 30 centimeters, 100 megahertz is 3 meters, and 10 megahertz will be 30 meters. 100 megahertz, 3 meters, right? And 1 gigahertz is 30 centimeters, 10 gigahertz, 3 centimeters. All these pretty large wavelengths. Well, maybe let's do a 5 gigahertz because that's the kind of wave frequencies we use quite often in our day-to-day communications. For example, cable TV. Who knows the frequencies that come in cable, coaxial cable, if you have a coax cable, not the dish, coax cable coming to your homes? What frequencies are those TV channels at? What? 30? Yeah, that's similar. I think there might be some channel. I don't know exact, but what I looked up was around 50, 54. Some channels I found even at 100. So I found them in the range of, but there could be some at 30, which I may not have found. So they are between this range, 50 to 200 megahertz. So let's just call it 100 megahertz, which is 3 meters wavelength. Okay, I want to focus you to focus on that. So a single conductor waveguide could not be used to bring that frequency to your home. And it's true for actually an optical fiber also. You don't have, if you did not have metallic waveguide, if you choose to use optical fiber, you could not have brought this signal to your home. How's optical fibers bringing that signal to your home then? Let me ask you. So coax cable is a different thing. Coax cable can bring this signal to your home. But we also get signals from optical on optical fibers nowadays. You don't have to have. How do we get that?
Is it because they also use like the phase information as well?
It's not related to phase. So let me tell you this. So cable TV, the channel will be, let's say, at 50 megahertz, but the bandwidth of one channel that, let's say, you want to watch some some HBO or something, that channel might be in a very small range of frequencies. But anyhow, if it's not related to the phase, how can an optical fiber bring your TV signals at these frequencies to your home? Yes?
The light itself is at a much higher frequency. It's just the digital signal is at that frequency.
Yes, exactly. First of all, I think if those are not analog, so that's called modulation. Even it may not be so your signal may be at few megahertz, which means few megabits per second if you convert it to digital signal. But the light frequency itself, which is coming in the fiber, is 1.55 micron. It's about 200 terahertz. This is megahertz. It's 200, around that. That's 1 terahertz is 10 to the 12. So that's 1 million megahertz. So the carrier, that's called the carrier frequency of the radiation that brings, is much higher. That's why fiber as a waveguide can bring it to you there. So that's just, I want to just kind of bring you this notion that waveguides cannot bring you low frequency signal just because of the wavelength being too high. So there is something about waveguide dimension. The dimension is has to be of the order of the wavelength or larger for a waveguide, and in this case, single conductor waveguide. So and optical fibers can bring it because you are kind of piggybacking your signal onto the optical carrier frequency, right? Cable internet. I just want to. I looked it up earlier. Is just for you to know, it's the upload is around at this frequencies on if on a coaxial cable, and downloads are around these frequencies if you have coaxial cables. So I will talk about coaxial cables. That's why I'm mentioning these data points to you. There are some channels that I think are also in 500 to 700 megahertz range. So let's talk about the dimensions. The waveguide that we did was a rectangular cavity. So as I told you, this is a single piece of metal. You can carve it out, you can, from a single piece of metal, single conductor waveguide. So if you remember, we did something like to find the cutoff, the beta z, if this is the z direction, is omega naught square nr square over c naught square. So that's our beta. Okay, that's our beta square, and minus beta x square minus beta y square. So that's the beta z, and this must be real. So I want to write this expression in a slightly different way. First thing is I want to rewrite this as, so this is beta, right? Beta is omega naught over c naught n sub r. But you can also write it like 2 pi over lambda n sub r. N sub r is, what is n sub r? Refractive index of what? The medium of the waveguide, n sub r. So this beta is 2 pi over lambda medium. Let me call this lambda medium, where lambda medium I'm going to define as lambda, the wavelength that you are passing, divided by n sub r. This is a common way. The lambda inside a medium is the lambda that we are launching divided by the refractive index, right? So let me write this in a slightly different way. I can write my beta z as something called 1 over or 2 pi over lambda z. I can call my beta x as 2 pi over lambda x. call my beta y as 2 pi over lambda y. And my beta is obviously 2 pi over lambda medium, inside the medium. Why am I doing this? If I do this, what do I get? I get 2 pi whole square over lambda z square equals to 2 pi square over lambda medium. This is the entire wavelength square minus 2 pi square over lambda x square minus 2 pi square over lambda y square. So what have I done? I have converted this relation. Remember, this was a relation beta square equals to beta x square plus beta y square plus beta z square. I have converted this relation to, I get rid of all the 2 pi's on the numerator. And what do I get? 1 over lambda medium square equals to 1 over lambda x square plus 1 over lambda y square plus 1 over lambda z square. So lambda medium is the wavelength inside this medium. So if you have a, just like he was talking yesterday, 600 nanometers orange light. If orange light goes inside water, which is an index of 1.33, well, that will be around 400, I guess, nanometers inside water. So that's the lambda medium. So if I launch this mode, so this is for a particular mode, there is some variation along x for the mode, right? You all know it goes up and low. So that variation defines the wavelength along x. So this variation I can call as lambda x. So as you mentioned one time, this is the first mode is half wavelength. So this is this kind of this shows you this is half. The lambda x is 2a in that case. Okay, when you have TE20 mode, lambda x will be a. So this tells us, well, let me not say this is lambda x. This tells us this dimension gives us lambda x, proportionality to lambda x. It could be multiple times of half lambda x. Okay, this dimension. So maybe I should not show the mode like this. I should just say that this dimension along the x is lambda x. If this was x direction, this was y. So I will just draw a wave like this, and this tells us about lambda x. This tells us about lambda y. And then there is a wave which goes along as lambda z. So here, if I go back to my picture from last time, what is lambda x for this mode? Again, lambda x, along x, what's the wavelength for this mode?
Oh, 2A?
2a. Can everyone see why 2a? Because this is half lambda. So that means lambda x is 2a. What's wavelength along y? What's lambda y for this TE10 mode? Is it changing at all? Lambda y is not 0, infinity. It's infinity. What's lambda z? Lambda z is whatever is left over. So their square added together, their inverse, has to be 1 over lambda medium. But whichever mode you take, the higher order modes will have some lambda in there. So in other words, it's a little bit hard to, it's kind of like a combination of resistors in series. The lambdas, what lambda x would be and lambda y would be and lambda z would be, they have this inverse relation. So as you go to higher and higher order modes, this number, so for the, okay, let me write that down. TE10 mode. TE10 mode will have lambda x as 2a, lambda y as infinity, and then lambda z would be, you can calculate from this, 1 over lambda medium, 1 over lambda medium square minus 1 over 2a square. Okay, so that's an example. So from this expression, what I want to show you is which of these quantities, there are 4 quantities here, which of them is the smallest? Yes, Mari.
1 over lambda y squared.
No, in general for any mode, not, I'm not talking about the inverse. I'm talking about which of lambda x, lambda y, lambda z, or lambda medium the smallest. Lambda x is the smallest for any general mode. Anybody? That's not true. Yes, Randall. Lambda z is the smallest.
I'm going to say medium.
Medium. You're saying medium. Anybody?
It's kind of like when you do the.
That's why I'm bringing that up. The resistors in series. Think of these as 3 resistors. If you combine 3 resistors, no, not in series. Sorry, parallel. Okay, okay. Three resistors in parallel. What's the equivalent resistance? This is the smallest. So which is the smallest of them? So, this expression, I hope, can help you understand that that all of the lambda x's, lambda y, and lambda z, all these 3 quantities are larger than lambda medium. Okay, does that make sense? Lambda medium is related to the frequency we want to launch in the waveguide. All these lambdas are larger. It can be infinity, but in general they have to be larger. And the dimension, what's the minimum dimension you can have? What's the minimum A you can have? Lambda x by 2, right? Can you have it smaller than lambda x by 2 for supporting this mode? No. So which means there is a restriction on the geometry. This is a different way of thinking. You cannot have a dimension of a geometry smaller than lambda x or lambda y or lambda z, or for in this case lambda x and lambda y, and those itself are larger than lambda medium. So in other words, if I had to do just a hand waving argument, you can kind of see that the geometry, the dimension, have to be smaller than half of the wavelength. Is that yes, right? So A, I have to say, is or I myself, let me go to the next page. So A, the waveguide width in general is m lambda x by 2. So basically it's greater than or equal to lambda x by 2. B equals to n lambda y by 2 for the, so that means it's greater than or equal to lambda y by 2. So now if we go, so we can say that lambda, it has to be bigger, not smaller. I misspoke. It has to be bigger than half lambda medium, and B has to be greater than or equal to half lambda medium. So the smallest, this is kind of a just hand waving argument, smallest cross section of a waveguide will be approximately uh, you choose a cross section in which the dimension is lambda medium by 2 on this side and lambda medium by 2. And obviously the other dimension is infinity, right? It's going infinite length. And lambda medium by 2 is basically lambda over nr, the refractive index. So lambda over 2 nr, this is lambda over 2 nr. So this is just something to know, that the smallest waveguide you can make to transmit a lambda has to be of this cross section. So again, coming back to our TV signal for 100 megahertz, 100 megahertz is 3-meter wavelength. So if you have to choose a single conductor transmission line, you have to have about, if it was air filled, for example, half meter. So that's a very large waveguide. If you were on so for example, I remember F-35 or some the plane that has a radar on it for detecting some objects to launch a missile. I think they use 30 or 40 gigahertz, somewhere around that range for the frequency. So 1 gigahertz is 30 centimeters, 10 gigahertz is 3 centimeters, 50 gigahertz would be divide by 3, so around 1 centimeter. Still, if you were dealing with those kind of frequencies around 30-40 gigahertz, you would still need centimeter sized components on there, which is not possible. So single conductor, so this is true for single conductor waveguides. So what's the answer? How can we channel signals or EM signals at small frequencies or large wavelengths? So this is a very actually you may never think about. You can use a printed circuit board, or you can do experiments in ECE121, and you can channel 10 megahertz. That your current and voltages is nothing but actually electromagnetic fields. It's a way that there is a field around your wires. It's electromagnetic wave that's going along the wires. You can also channel 10 kilohertz or 1 kilohertz. And those wavelengths are meters or hundreds of meters, the wavelength of. So let's say if you are doing an AC signal in your circuit, which is at not 1 megahertz. So let's pick an example. I just want you to have some realistic number in mind. Instead of 10 megahertz, 10 kilohertz. So we'll have, for 10 kilohertz, what will be the wavelength? Shan, what will be the wavelength for 10 kilohertz if you just look at that table and not calculate? What? Yes.
30 kilometer?
Yes, exactly. 30-kilometer wavelength. So when you are doing in a circuit and you are launching an AC source in that circuit with a signal generator at 10 kilohertz, the wavelength of fields that is around those wires is 30 kilometers. You never think about wavelength that way, but it is. How is it that you are able to use wires to channel that 30-kilometer wavelength field? Why is it that? Why does this limitation not come into play? Anybody? You're changing the potential, but there's still field in your circuit. If you had some instrument that can, or a camera that can visualize field, there is field around your wires. It's not as if there is no field. Uh, your wires are encapsulated with a dielectric or some plastic, but that does not mean the field does not go. There is field all around those wires. How is it that your wires are able to channel? So that is something that forms the basis for what we are doing next. That if you release this limitation of a single conductor, you make multiple conductors, you can actually have a dimension of this waveguide which is smaller than wavelength. So your circuit, let me write it this way, ECE201 circuits are actually waveguides, or the wires are waveguides, with one difference. The difference is they are multiple conductor waveguides. So let me draw a kind of a snapshot. There are multiple conductor waveguides, and we don't call them, first of all, we call them transmission lines. Now, when you study in 123 or 121, people don't use them, this terminology, because you don't necessarily need to use it, because we don't deal with fields that much, and we don't want to, this is more complex to think about. And we just deal with currents and voltages and Ohm's law. And that's something called lumped circuit approximation that we are working in. And so we don't have to think about it. But I want slowly, as I am going along, you to tie in that thing that you do in circuits with what we are going to do. If you can tie this in nicely, it will really enhance your knowledge of what's going on in this wire. So let me just, so this statement, I want you to, for now, take it for granted. These are our circuits that were used with the wires are actually waveguides of radiation. They do carry radiation at that 30-kilometer wavelength. But they have multiple conductors. So they are multiple conductor waveguides, and instead of calling them waveguides, we call them transmission lines. So where are those multiple conductors? If your circuit, so let's talk about a very simple circuit. This is your V in AC signal. Then you connect, then you have a circuit, an op-amp circuit, let's say. You connect your circuit, your audio amplifier, or whatever you may have. And then it will have a load. This is load. So where are the, I told you there are multiple conductors. Which one are the multiple conductors here in this circuit? Is it a single conductor or multiple conductors? Wire 1, wire 2. These are multiple. So this is a waveguide. And this is not a single metal wire. There is a discontinuity there, and there is a discontinuity there. They are not connected together. They are at the same potential. So this is a waveguide. This is conductor 1, C1. This is conductor 2, C2. We can call this C1, C2 also, maybe, or C3, C4. This is a waveguide or transmission line. So I'm going to call it TL. This is also a transmission line. And this is, in general, the most common transmission line. Most common transmission lines are made up of two conductors.
Doesn't the coax kind of look like this, where they're like the two?
Coax looks like this. I'm going to show you the picture. Yes. Yeah, exactly. So now the question is, the reason I'm asking you to tie this in with, sometimes, what is this symbol for? That's the symbol I used to use when I took my course. What is this symbol that I just drew? Ground, right. Okay, so I just want to make sure we are all on same page about, so there is a circuit here which will have its own ground, and then we will have this conductor, let's say an RL. So that's R load. So that's typical how you connect circuit and solve it. In this case, there is only one conductor. Where is the second conductor? What? Yeah.
To ground.
Yeah. Where is that conductor? So there is one conductor here. This ground is the second conductor. So that exactly that I just want to show you. So there, the second conductor is this ground, which is C2. There is a second conductor. So if I'm connecting my wire, if you're on your PCB, you put in a wire on one of the holes, you take it all the way to your circuit. On the other side, this is one conductor, but the other conductor is under the PCB, which you don't see, the ground plane. So there are always two conductors when you are transferring electromagnetic energy or electrical energy. Voltages and currents are associated with electromagnetic fields always. There's always going to be. And please think that there are always two conductors. Don't forget so you can never have a single wire plugged in here and take the current to the other side. You always have to close the loop. And that loop means there is always this two conductor path for the wave to travel. You can never have a one conductor. If someone tells you I'm using a one conductor to transmit my electrical current or voltage or field, it's not possible. So two conductors is a minimum that's needed at these frequencies. Otherwise, you can do with, so I have to qualify. You can use one conductor, but then its dimension has to be of the order of the wavelength or larger. That metal waveguide that we did was a single conductor. It can carry, but our dimension has to be much larger. So let me show you the pictures of the so these are some types of different cables. These are Ethernet cables. They're used to transmit data at to 100 megahertz. But 100 megahertz, as I said, is 3 meters. Each of these cables, so these are, they're standards, and each of them is Cat7, maybe not even the recent standard. It can actually do gigabits per second. In general, when you connect an Ethernet cable, it can probably do 100 megabits per second up to that speed, which means its frequency that you transmit is of the order of 100 megahertz, but you can also go to 1 gigahertz. But do you see, so there are 4 transmission lines bundled into this, 4 Ethernet cables bundled into this Cat7 cable. And obviously, the dimension of that cable is not of the order of wavelength. And each one of them is this. So there are 4 transmission lines. That's how it is made. Each one of them, each transmission line here, this is Cat7 cable is transmission line, is 2 conductors, you can see. 2 is the minimum you need. In this case, each of these 2 conductors are surrounded by, let's say, Teflon or some other material, which is a dielectric. They can be twisted or not twisted. And then they are surrounded by another foil. This foil is a metal. This is a third conductor. It's not actually used to conduct. What's the purpose of this? Does anyone know? Shield. Exactly, shield. So that this field from here, data or field from here does not leak into or match into. Remember, we are transmitting 100 megahertz, which is 3 meters wavelength. So the field, if we did not have this shield, can actually extend very much into air. So this shield helps us to neutralize and not have the field leak out. So you mentioned about coax cable. That's the, so I'll post this. This is the coax cable geometry that comes in your homes if you were using a coax cable. There is a center conductor, then there is some sort of dielectric, And then there is this foil, which is actually used in this case as the second conductor. And then there is also this shield for preventing interference with this, with outer signals. And then there is another outer jacket of some polymer or plastic. And it turns out it's two conductors, and that's it. There is no field leaking out. It can carry signals which are at 100 megahertz, 1 megahertz, or even lower, and you don't need its dimension to be of the order of the wavelength. How does it work? That's the purpose of chapters 11 and 12. How can we model this transmission line and kind of a comprehensive model which works at all frequencies. We don't need to model this if we were only working at lower frequencies. So if you were working at frequencies that you deal with in 123, 121, 100 kilohertz, 1 megahertz, maybe 10 megahertz, your op-amp circuits, even 100 megahertz, you don't have to worry about modeling this as a transmission line. The reason is the wavelength is much larger. So, but once you get to higher and higher frequency, there's something else that starts to come into play. What is that? So I'll show you that later. We'll come back to that later. I guess if we have a ground connection here, we have this wire, and we have a ground connection here. And somebody applied a voltage source V1 here, V1 sine omega t. So I'm going to call it V1 phasor, right? When I say phasor, that means it's a sinusoidal quantity. What do you learn in 123? What is V2? And the length is, this wire is length L. What is V2? There is nothing in between, and there is ground. You just take a wire, it's V1. Right? There is no potential drop. We are not assuming this wire is resistive, so there is no resistive drop. But what if I said that it's not V1, it's actually V1 times some quantity? Okay, maybe not C e to the j theta. And you will be saying, well, why are we introducing another complication in our life? we deal with circuits, that's enough, and we solve circuits, and we have plenty of circuits and put transistors in there and wires connecting transistors, and then we have a hard time solving those circuits, and we use Ohm's law. We ignore those wires. In your simulations, you can make those wires as long as you want, as short as you want, and not just simulations. If you're actually building the circuit on a printed circuit board, do you ever worry about whether I should pick a small wire or a long wire? Not much, right? And that's the reason is that wires don't matter. The voltage from one end is the same. But they start mattering. When do they start mattering here? When do they start to matter? Not mattering. When do they start to matter? But the length in ECE201, 123, our length is much smaller than lambda. This thing is called lumped circuit approximation. Have you heard of this before? Lumped circuit, what? Yeah. So lumped circuit approximation. When your length of the wires, your length of the whole, your dimension of the whole circuit is much smaller than the wavelength that you're dealing with, you can, in that case, C equals to 1 and theta equals to 0 or 2 pi even. But if L is of the order of the wavelength or larger, then it's no longer true. C is not equal to 1. So I have to say that C will be less than 1. It cannot be greater than. You cannot amplify a signal just by a wire. And theta will not be 0. So when will that be the case? If you were joining Intel as a circuit designer, when will this happen? When you were working, if you were to work on circuits as a designer, when will you start worrying about things that you learn in 203? If you join a circuit designer, there are situations where you don't have to worry about 203 stuff that we are going to learn, or you will have to worry about 203 stuff. When you have to worry about 203 is when this C is not 1. What is this situation? You want to tell me? Based on looking at that. Look at this. What kind of a circuit would you be working on? Just the answer is in this statement right here. Yes?
Would it be when you have really long wires?
Pretty long wires, that's a good. But usually when you are doing a circuit design on a PCB, which means your circuit is of a certain dimension. So you won't start making a circuit which extends across a table, right? What is the other? No, somebody else? Yes.
Extremely high frequency.
Yeah, exactly. So it's very simple. Lambda is smaller. If you start going to make a circuit for your cell phones, if you join a company, Broadcom or some other company which is making circuits for your cell phones, your cell phone is generating signals at 5 gigahertz. Those are called the, I guess, the circuits which are at the, maybe transceiver circuits or at the front end or something like, which deal at such high frequencies. Those, when your lambda gets shorter, when your frequency gets higher, so this is the case when F is very high or lambda is small. So 5 gigahertz, as I told to you, let's look at that table. 5 gigahertz is 6 centimeters. Now, if you are making a chip, which is 1 millimeter or maybe 1 centimeter wide, if you're designing a circuit on a 1 centimeter chip, you can say, well, that's still smaller than 6. So within that chip, maybe you still may not introduce too much error. But when your chip is talking to another chip, there's interconnects. Those interconnects can be of the order of a centimeter. Or when your chip on this system is talking to another computer on a data center, there's wires connecting them. That's when your wavelengths are no longer, your lengths of the cable is no longer. So when today, all of you, most of you, when you go to, even if you're working on low frequency circuits, you might have to deal with somebody who is working on high frequency because everything is going to higher speeds, higher frequencies. You have to know this stuff. So don't sleep through this, and please try to understand. This is very important stuff, okay? Transmission lines. We need to understand how to deal with transmission lines when the frequency become higher, how to know what is C and what is theta. Yes?
So when you're talking about the high frequency, like designing boards, does that have to do with kind of like receiving it or like like putting out an analog signal, or is it?
It doesn't matter. It could be digital or analog.
Okay.
What is the digital signal? When you say you have 1 gigabits per second, let's not even go to 1 giga. Well, Yeah, well, we will go to 1 gigahertz per second because that's when the frequency really becomes. That, first of all, that means if you have to use a 1 gigabits per second, the way you do analog to digital or modulation and you generate digital signal is either you can just have your voltage, this is voltage with time, just go like this, right? So the time difference between the shortest pulse would be 1 gigahertz is 1 nanosecond in terms of time period. So the shortest time period you will have is 1 nanosecond. If you look at its Fourier transform, this is your time domain signal. So if you look at its Fourier transform, V of f, if this is f, so this signal, this, if you're transmitting just this on and off voltage signal on a wire, this will be around 1 gigahertz and maybe have some sort of signal like that. So that's what right here. If you're going 1 gigabits per second on a wire, your frequency components are at that frequency. Yeah. So this C is not equal to 1, and this we need to learn, and I can guarantee you if you pay attention, you'll have at least a formative understanding of how to deal with this stuff at higher frequency or in general. So chapter 11 is field analysis of transmission lines. There's a bit of math and too much of math here, which we can spend a whole lot, and it does not bring out the intuitive understanding. So I am going to do only chapter 11 in bare minimum math just to understand. Chapter 12 is circuit analysis. Circuit analysis of transmission lines. It turns out these are waveguides. We're doing electromagnetic waves. But we, instead of now dealing with E and H fields like we did in waveguides, we can actually deal with voltages and currents, which you should be a little more comfortable about. So we can actually start working with voltages and currents, which you know from before, but we still transmit our waves. These are electromagnetic waves. So in the transmission line, so this is how the fields look like when you have two wires going parallel. And one wire has, so for example, if you made this circuit, a voltage, and then a wire and a resistor here. This is wire 1, or in other words, I'm going to call this 1 and 2. So you are looking at a cross section of conductor 1 and 2. Standing here, you chop this off. These are wires, thick wires. Okay, that's what I'm showing here. 2 wires, and then you have your load. And when the signal is going, you probably never thought about this much. What's going on between the wires is their field. As I told you, this is 10 kilohertz or 1 megahertz. There is current flowing through these wires. There is a current I going here and current I going back. And I'm going to put it as a phasor because there's a voltage which is a phasor. What's I? What's I in this circuit? Can anyone tell me? V over R. Exactly. Not in 203 though. I is V over R in ECE203, but not in 203. Okay, so we will find out. So what's happening in general, even in 123, even in ECE123, this is what's happening. If somebody was, if they wanted to, they could have showed you how the electric field and the magnetic field looks around the wire. So even the wires that you connect on PCB boards, they have this kind of field around the wires. Solid lines are E field, dashed lines are H field, and remember what I told you. the lines, the field is along the lines. That's the lines show the direction of the field, and what shows the magnitude of the field in this kind of a diagram?
Is how close they are.
How close they are. I'm not sure if you can kind of see that very much here, and probably not. But how dense you make those lines shows you if they're stronger field or not strong. And as you can see, you will never find E field which is tangential to any conductor. Tangential E field is 0. Normal H field is 0 always. So there is no tangential solid line. There is no normal dash line. H field always encircles a conductor. You have learned that what is called Ampere's law. The current is going in a wire. H field is your like fingers. H field always encircles conductor. E field always goes normal to the conductor. So that's the field in your wires, and this is how the field looks like in the coax cable. This is the shield. This is the center conductor. These are solid lines. These are pictures from your book, by the way. These are solid lines. These are E field is going radially out. And dashed lines are magnetic fields. So magnetic fields are just is surrounding that central wire. So I'll put these figures also just in case to the note today. So that's where we will we'll start with some discussion on in chapter 11 to understand our to form some basis, and then real stuff that we will do, the math that we'll do is in chapter 12. One last thing is there are a few things associated with the transmission lines, and let me point that out. And if you want to read ahead on this, CLRG, 4 parameters. And these are farads per meter, Henry per meter, ohms per meter. So this is not the R is not the traditional resistance in this symbol. It's not ohms, but this is ohms per meter, and this is Siemens per meter, which is actually per ohm per meter. And at some point they started using that symbol. Have you seen that before? 1/1 over O. I read it, but I don't think it's adopted. And it was called Mo, which is 1/O.
Bro, whoever, someone was just really lazy. I know. This was not copy and paste from some stupid.
Okay, it's not stupid because I think they did. Now you may have to do a Google search and find out, but I did. Somebody, at least my teacher, when I learned, they use this symbol if I remember right. Now that could be, but Siemens is a, and then Z naught is. You will also learn about Z naught. That's in ohms. That's characteristic impedance. These are few parameters which we will talk about a lot. These are called primary parameters of transmission lines. And these are capacitance, inductance, resistance, and what else? What is G? C, L, R, and G. What is G? Siemens per conductance per unit length. So if you want to read up a little bit, try to read up, and that will help you to understand more in a better way. So that's it. See you next week.